Good morning, everybody. Got to get started. It's 11:10. If you have questions, I'm here for half an hour after class for office hour. I'm happy to help people with technical questions or anything that's going on. Just a reminder, what we're going to do today is kind of finish off chapter 4. I'm not sure how far I'm going to get. If there's one final example with pulleys, I might end up doing that on Friday, and then we'll be done with chapter 4 and all the testable material for your term test coming up. But let's get things rolling, shall we, with a little chapter 4 type question on learning catalytics. Just thinking about normal force, again being a self-adjusting force. So give me a minute. This is pretty straightforward. Give you 1 minute to think, pair, share. Ten seconds. Click in an answer. Okay, time's up. Going once, going twice. All right. So, 67%. The idea here being that the tension force is part of what is supporting the box. So if you were to draw, let's draw it out, shall we? Grab my handy dandy pencil. So that's a sketch of the situation. If you were to draw a force diagram, it would look like this. There would be normal force going up of, I guess, the surface on the box. The tension going up and to the right, which is the surface on the box, which would have components, a y component and an x component. There would be friction of the surface on the box, and there'd be the gravity of the Earth on the box. They're all on the box, which is good because you're drawing the force diagram of the box. So all these have to be external forces of some other object acting on the box. And a sub x equals 0, so you can define y is up, x is to the right, ax is 0, ay is 0. So you have to balance all these forces. And there's going to be something like the sum of all the forces in the y direction is equal to 0. It's going to be normal plus ty, if this is ty and this is tx, minus mg. So you'd say that normal is equal to mg minus t sub y, which is less than mg. Make sense? So that should be, don't just memorize the equation for normal force as mg. It often is mg, I'll admit that, because like if a box is just sitting at rest on a table, then and it's not accelerating, then there's two forces acting on it, normal force and gravity. And so to balance things out, the normal force often comes to be equal to mg. But it's not a good equation to memorize. Okay, so that's a good start. Don't forget, there's a term test coming up on Tuesday. This is the day after Thanksgiving, as soon as you come back. It's in the evening. These are the rooms that you go to. There's 5 rooms within 255 McCall Street. There's one kind of in the basement, that's EX100. There's one sort of on the main floor up a couple stairs, that's EX200. And if you're in one of the 300, 320, or 310, you have to go kind of upstairs and find your room at the top floor there. And there's tons of, I think you might even see some of your TAs, they're actually invigilating, walking around and staring at you or whatever. I will be there. I'll be wandering around through the rooms just to kind of make sure everything's going smoothly. If you have accommodations or if you have alternate sitting or something, then this is not your room. This would be, you have instructions, follow those instructions. So one of the things that happens in a big term test like this is that the invigilators have a signature sheet with your name on it and a blank beside it. And they walk around and every single student has to sign their name beside their name. And then we check your T card. You don't have to take off your mask. We'll just check the T card with your eyes if you want. But if you're in the wrong room, then you're not going to be on the signature list, and it's going to be a problem. And so what will have to happen is you'll say, well, what is your last name? And then they'll know what room you're supposed to be in. You're going to have to pack up all your stuff, walk with the invigilator, find your other room, be dropped off, and it's going to take some minutes out of your test, and it's be kind of embarrassing. So try to get your right room, if you can. Just other little things, covers chapters 1 through 4, including the stuff we're doing today. And maybe a little bit on Friday if I can't get through this pulley example today. There will be 10 multiple choice questions for which you bubble out the answer on one side of your answer sheet. And then one written question, you flip it over and actually write out your answer. Both of those are going to be scanned actually, and the bubble sheet is marked automatically, but the written answer is marked by a human being. There's a poor TA that I've been talking with about this who has got 24 hours of time over this week to go through and mark every single student's test, read it through, show that you've, confirm that you've done the reasoning. So on the one hand, just getting the correct answer without showing your reasoning will not get you full points. You have to show what your steps are, basically, so that this marker, who's working on his PhD in physics and is a pretty smart guy, but needs to see what you've done, right? But conversely, if you get the wrong answer, but you've done a bunch of right steps, there's a bunch of partial credit that he's going to award for showing that you've drawn a diagram, they've got a force diagram, you've set up some Newton's laws. Something might have went awry when it came to plugging in the numbers and you got the wrong numerical answer. You can still get like 80% or something just from writing down all the right steps. So you get points for doing correct steps in this whole method that we've been talking about. You need a calculator, something like that, Casio. You are allowed to have a programmable calculator if you want one, but it's not required, and I don't think it will be all that useful. You're allowed an age sheet, one piece of paper that you can write anything you want on both sides. Examples, old test questions, whatever you want, okay? I would write the equations you need. That's the main thing. Anything you don't feel like memorizing that you use a lot in doing problems, you should write it on your age sheet. So I would write down these equations of constant acceleration and stuff. Question over here? Yeah, that's a really good question. So actually on Friday, I might as well just show you that first page that'll show the possibly helpful constants or something like G and anything else that you might need. If there was any coefficient of friction or any numbers like that, I will provide it to you. You don't have to write it on your age sheet, okay? That's a great question. Yes? Pen or pencil doesn't matter. They both scan. It's an optical scanner, so it picks up pencil just as well as pen. Maybe pencil's a bit better so you can erase if you want to. Yep. No, yeah, that's a great question as well. So the test, there'll be two things on your desk when you come in. There'll be the booklet with all the questions in it. You don't need to write on that. You can if you want. And then there's the answer sheet, which is the multiple choice on one side. You put the bubbles and you flip it over and write out your written answer on the other side. But you have to hand in both at the end just because we collect the booklets. But the only thing that's really marked is that answer sheet. All great questions. Over here, Madeline. Yeah, that's a great question. So the age sheet may be front and back side that you can write on both sides. And I'll talk more about the test and exactly what to expect during Friday's class if you're here. Maybe some like strategies I'll go through about test writing skills, what worked for me, like bring a snack. I always brought a banana to every term test that I ever wrote because I'd be like, I'd start to realize about halfway through the test that, oh my God, I'm halfway through this test. I'd start feeling that panicky feeling in my gut, and then I'd say, I know, I'll eat my banana. And so that I'd eat my banana, and somehow it always calmed me down. I don't know why, but just something about having rituals for me calms me down. Okay, let's look at this little video on projectile motion. This is to do with that last learning catalytics question I gave you. So one is dropped straight down and one is fired horizontally. They impact the floor simultaneously. Now, the orange one, if we can go back a little bit, has a higher speed at all times than the green one. They're tiny little blocks and they're shot by a spring. Maybe press pause right there. Its distance between its dots in the motion diagram is always bigger than it is for the green one, because the green one has no horizontal component of its velocity. This is always going on this diagonal. But in terms of just the y component, they're always equal, because v0y or something, the y component of the initial velocity, is actually the same for both. And that's that idea. So let's do, this is an example actually from your text, and it uses a trig identity. So by the way, in addition to numerical constants, if you were to need a trig identity, such as this one, I would put it on the possibly helpful information on the test. I don't expect you to write every trig identity on your aid sheet, but there's one. Okay. What is the angle you should throw a ball so that it travels the longest horizontal distance, assuming you throw it at the same initial speed? So what I'm going to do, by the way, is assume no. That's my favorite thing. Something about leaning on it. Thank you, Pius. This is my HDMI splitter stuff. Assume no air resistance. That's something that you can just write on this. But so sketch it. What I would do, so you've got something like that. It starts here. It goes some distance. It's got some initial V0. There's some angle here. And the idea, if I define y to be up and x to be to the right, is that the y final equals the y initial. It comes back down to the same height. So, and we can set that equal to 0, I guess, if we define the beginning to be the origin. And then you split this up so that you have V0y and V0x. So the way it goes usually is V0x is equal to V0 cosine theta. I'm not going to go through the whole right angle triangle, but I can tell you that. And that's just constant Vx. And V0y is V0 sine theta. So I'm getting that from analyzing a right angle triangle in which the initial velocity is the hypotenuse. And then there's the opposite and adjacent. You have to figure out the components. Okay. And the way that's going to work is I'm going to use, for the y components, I'm going to say that a sub y is equal to negative g. And let's use, I'm going to choose one of the equations of constant acceleration. The one I think I'll use today is y is equal to y0 plus v0 yt plus 1/2 a sub y t squared. That should be on your aid sheet, hopefully. You need that one. And in this case, it's going to be 0 is equal to 0 plus v0 sine theta t minus 1/2 g times t squared. So the way I like to do it is g is a positive number, 9.8, and if you define up to be plus y, then the y component of the acceleration is negative g, or negative 9.8. So you don't want to get too mixed up with the... So you can solve for t. Luckily, you can divide both sides by t. I think you end up with t is equal to 2 v0 times sine theta over g, if you work that all out. And then for the x component, it's much easier. It's a sub x equals 0. There's only one equation of 0 acceleration, and it's just this. X is equal to x0 plus v sub x times t. Easy. And I'll say that maybe x is 0 as well. So I just get x, which is actually what you're trying to make the biggest, is equal to 0 plus v 0 cos theta times t. And now what I'm going to do is I already solved for t from the y component, and when you do these projectile motion problems, the thing that's the same about the y component and the x component is the time. So you take this and go and plug it into right there. And then you get x equals v0 cos theta times 2 times v0 sine theta divided by g. And now I'm going to use this thingy over here, try to arrange it. So I've got v0 divided by g, I think. There's two v0s, so v0 squared divided by g times 2 sine theta cos theta. And that's when I realize I can use a trig identity so that I get that x, the distance, is equal to v0 squared times sine of 2 theta divided by g. So we can set, like alpha is 2 theta, and we know that sine of alpha is maximum, like 1, when alpha is 90 degrees. So x is maximum when theta is equal to 45 degrees, which is kind of a handy thing. If you neglect air resistance and you want to throw a tennis ball as far as you can, if you throw it sideways, it kind of hits the ground quickly. If you throw it straight up, it doesn't go anywhere. But if you throw it right at sort of 45 degrees, then it goes pretty far. So makes a bit of sense there. Once again, I'm throwing things in class. Don't throw things in class. There was a time I taught 3 years ago in Con Hall when I said, oh, I know a good way you could ask me a question, because I was having this problem that people weren't shouting loud enough I couldn't hear. Just write it on a piece of paper if you're in the balcony and just throw me a paper airplane with the question. But that got canceled because people were getting like paper airplanes in the eye and all this stuff, and it was bloodbath, terrible. Don't throw paper. I got told it's a safety issue, so okay. Let's do another learning catalytics question while we're at it. See if you guys, I've told you guys this one a million times, so let's see if you remember. Give you a minute. If you don't remember, ask your neighbor. Give you a minute. That's your minute. You guys remember this one? This is almost a review. Let's see. Going once, going twice. Let's Still clicking in. I got 441 responses. So people good? 451. And stop. Laptop 2. Okay, it's sort of 50-50. B versus D. I wish I wouldn't put it green like that, because then it tells me what I thought. But B was kinetic friction, and D was static friction. So actually, I like that you all answered friction. That's absolutely correct. Friction is a horizontal force, unlike gravity, so it can get it going, parallel to the ground. So I like that. So really the big dilemma here is whether it's static friction or kinetic friction. So I have a lot to say about that today. Okay, I think you're all on the right track here. I'll circle this. I believe it's static friction, and I will say something about, let's discuss this, because it's not at all obvious. The thing's moving, right? Okay. So first of all, I think you guys understand this, but let me go through it quickly. Some people think that it's the engine which gets it going somehow. However, the engine is inside the car. So at most, the engine can only provide internal forces on the car. It's kind of like pulling yourself up by your own bootstraps or something. You can't accelerate that way. The only way to accelerate is if you have an external force on you from some other object. And that's clearly happening in this car. So it's not the engine. What does the engine do? Well, the engine rotates the wheels. It pushes backward on the ground, so that there's a little arrow there showing the angular acceleration of the back wheel on this car. And then there's a forward force of friction from the ground on the wheel. And this is responsible for the forward push, and it's friction of the road on the car's tires. I think most of you are pretty comfortable with the idea that it's friction. So I'm going to move on and say, why is it static and not kinetic? That's a great question. And I think at the end of last class, do you remember I said that no matter how fast your car is going on a highway, there's always 4 points on your car which are at rest. And that's the bottoms of the 4 tires. Believe it or not. This is known as rolling without slipping. So bear with me. Here's something to think about, something to consider, is that think about a tank and the treads on a tank. What happens is that there's all these wheels, and as the tank moves along, it's laying down some sort of conveyor belt almost, and sometimes there's even spikes on the conveyor belt to give it really good traction that dig into the ground, and then the tank rolls over. But think about the bottom of that tank tread. While the tank is moving over it, those spikes are drilled into the ground, and so they're not moving. They're at rest. The bottom of any wheel that's rolling without slipping is at rest. That's what I'm trying to convince you of. Another way of thinking about it is this triangle. You can imagine rotating the triangle, and the bottom of the triangle is at rest. See? It's turning, but that point at the bottom of the triangle is not moving. So that's 3 sides. Well, what if you did 4 sides and rotated a square? The bottom is still not moving. Well, what if you did 8 sides? Stop sign. Okay, the bottom is not moving. Okay, you got it? And then et cetera, et cetera. If you have an infinite number of sides of a circle, then at any instant, the bottom of the circle is not moving. It's just rotating around that point. If you can believe me. I think that's all I'll say about that. And what I think about it is that on my bike, if it's going along, the tread on my bike is it's being laid down almost like a tank. So at the very bottom, it's not an exact point, right? It's a bit squishy. So at the bottom, it's at rest. And if it was sliding for kinetic friction, then This actually happened to me today because a car cut me off on the way. I slammed on the brakes and my bike was going like skidding along and making this sound. Or if there was a car doing it, it would go like that. That's kinetic friction. Okay? Because then the bottoms of the wheels are actually sliding along the road. So if there's kinetic friction, you're in a lot of trouble. Okay? It means that you're about to wipe out or somebody just cut you off or something like that. In normal, car driving scenarios, you're not screeching your tires, right? So that means you're rolling without slipping, and it's static friction, not kinetic friction, that is responsible for this external force. So hopefully that helps. Let's do this question. You guys are going to love this. I'm going to do 2 questions about the exact same situation. Now this, in the previous car, it had what is called rear-wheel drive. But in some cars, they have all-wheel drive, and in some cars, they have front-wheel drive. Front-wheel drive is actually fairly common. The engine is closer to the front wheels, so it's only connected to the front 2 wheels. The engine torques the front 2 wheels, and the back 2 wheels just roll freely along the ground. So my question is, if the car is accelerating towards the right, what is the direction of the force of static friction of the road upon the front wheels? 1 minute. I'm going to ask you about the backwards. So a student just was asking which way, so the torque is turning the wheel clockwise. So sometimes when I think about the force of static friction, I think about the 2 surfaces. Which way does the object want to slide if it was frictionless? Well, the static friction is opposite that, to prevent it from sliding. So you got to think about if it was an icy road and these wheels were accelerating because of this torque, which is a future concept I'm going to talk about in a couple weeks. Which way would the wheel want to slip? Okay, so and static friction should be opposite to that. Going once, going twice. Top 2. So sort of a bit of both. So this is that external force I talked about, which is accelerating the entire car. This is a huge force. The wheel wants to slip backwards. If it was icy, you can imagine stepping on the gas, your wheel would be accelerating clockwise, and it would be slipping, that surface would be slipping backwards on the road. So static friction prevents it from slipping by pushing forward on it. And luckily, that's what makes your whole car go. Not luck. It's by design. So second question, very similar to this last one, exact same situation. What about the back wheels? Give you another minute. Oh dear. You got to press send to all. Well, maybe I'll just leave that one on. And so the question is, some of you may have seen the answer to this. So the question is, why does Harlow think that it's backwards? Okay. Sort of screwed that one up. Okay, so the car is accelerating due to some forward static friction, big force here. And what that does is it drags the axle. Axle is connected to the car. And what I would say is that, whoops, the rear wheels, too cluttered up here. I'll just balance my water right on my laptop. No, over there. The rear wheels do rotate. I don't know if you've noticed this, but even if you have cars with front-wheel drive, you can't tell because all four wheels are rotating as the car is moving. So why is that? The rear wheels do rotate as the car accelerates. They roll without slipping. So now, the reason that the front wheels are rotating is because they're connected to the engine. The reason the back wheels are rotating, I think, is because they're getting dragged along the road. Like if you pull a wagon, the wheels rotate for a completely different reason. So this is due to a small backward. They want to slip forward in this case if they weren't rotating. So there's a small backward static friction force from the road. That's what I'm thinking. And it's just enough to spin a tire. It's as needed. And it's far less than the forward static friction force, spin a wheel, I guess, on the front tire, front wheel, which has to be enough to accelerate an entire 1-ton car. Anyway, so this is, and then let's do, since we're on rolling without slipping, let's do one more slide about this. This is coming from your textbook. This is kind of what happens as a tire, as a wheel rotates, is that this part goes down, makes a new contact. Then as the wheel rolls over, the tire is not moving in this little area here. It's not sliding. Kinetic friction always involves sliding of two surfaces. And then, so if the tire is moving and turning faster because of some torque on it, the engine torque, then what happens is that if the tire is turning faster, it pushes back harder on the road in turn pushes forward on the tire, causing the car to accelerate to the right. And also, you can put on the brakes. This will slow down the rotation of the car. This is the brakes. Brakes, torque. When you put on the brakes, there is a torque which slows the rotation of the wheel. So if the tire is turning slower, it actually is pulling forward on the road because the car's got its own inertia or momentum that kind of wants to keep going. So if the tire is slowing down because you've got the brakes on, it pulls forward on the road, so the road pushes backwards or pulls backwards on the bottoms of the tires, and that's what slows down the car, actually. And it all happens with static friction. All right. How are we doing for time? We're doing all right. So static friction, let's accept it, and now let's do a problem with it. So here's that table again of different coefficients of static friction and kinetic friction. Here's a question. What is the shortest possible amount of time that you can accelerate from 0 to 100 kilometers per hour, assuming you've got some static of friction, rubber tire on dry concrete? So let's use this one. So this might be given to you on the possible helpful information on the front of the term test. This is mu sub s equals that. Let's use that. 1. Let's use 1.0. Okay. Okay. So 0 to 100, we're going to define the system. Here's the car. We're going to draw it. Again, I always like in my sketch to draw something to just gather my thoughts. That's the first step. We can put a dashed line around the system. kind of helpful. Car, it doesn't say the mass, so let's just say its mass equals m. V0 is 0. V final is 100 kilometers divided by hours. This is, let's convert to meters per second. I don't really like that because I'm going to use G and stuff like that to meters per second. So I'm going to say that V is equal to 100 kilometers per hour times 1,000 meters in 1 kilometer times 1 hour is 60 minutes times 1 minute is 60 seconds. So the reason I've done that is because I want kilometers to cancel kilometers, hours to cancel hours, and minutes to cancel minutes. So all we are left with is the meters and the seconds. So if I times it all out, I get V is equal to 27.8 meters per second. I times by 1,000, divided by 60, and then divided by 60 again. Okay, and what I'm going to say here is that this is static friction. Because it's rolling without slipping. This is defined y up, x to the left. Neglect air resistance, maybe that's another good thing to do. So I can draw a force diagram. I've got normal force, I've got Fs, and I've got mg, something like that. And I know, I'm just going to write over to the side here that it's accelerating towards the right. So there's a net the net force is in the same direction as the acceleration, but I'm careful, I never draw the net force on the force diagram because the net force is just the sum of all the forces on the force diagram, right? So I just draw sometimes the acceleration off to the side. And again, what I'm going to do here is say that assume rubber tire and dry concrete, so that mu sub s equals 1.0 and f sub s equals f sub s max for the maximum acceleration you can get just before you start skidding, right? So some of the forces in the y direction is equal to 0 because ay is 0, and that is normal force minus mg. So hey, look, n equals mg. That's okay. But the reason n equals mg is because the y forces are just n and mg, and they cancel out. Then the sum of the forces in the x direction is equal to, I guess, just fs max, which is going to be mu sub s times n, which we have. So I'm going to take, once again, take this from the y component and plug it in to that. And I get mu sub s times m times g. So this is, so a sub x is equal to the sum of forces in the x direction divided by mass. Mu sub s times mass times g divided by mass. Oh, good. I didn't know the mass, and luckily it cancels. That's lucky. So if you don't know something, just define a symbol, and then cross your fingers, and maybe after you do all the math, the thing you don't know will cancel out. So it's called getting lucky. U sub s times g. We have both those numbers at 1.0 times 9.8. So it's 9.8 meters per second squared is the maximum you can accelerate a car. And then I can just use v is equal to v0x plus a sub x times t. I'm trying to solve for t. This is the worst handwriting in the world. Let me try that again. Sorry. It is v0x plus a sub x times t. That's one of the equations of constant acceleration. So t is equal to, this one's 0, vx over g, 27.8 meters per second. We converted nicely. divided by 9.8, and you get 2.8 seconds. And by the way, I looked it up, and a Bugatti can do it in 2.3. So how's that possible? Well, I think, and actually, my mother once dated a guy who was a race car driver, and he drove his race car up into our driveway one time, and it was covered in all these dry leaves. It was the fall, I guess. And I was like, what's going on? Why are there leaves all over your tire? And he said it's because the tires are sticky to increase this maximum static friction force. So actually, you can get mu sub s greater than 1. As you're actually kind of clinging to the road somehow. So you'd think 1 would be the most, but you can have mu sub s greater than 1, I guess. So you can really accelerate faster. Okay, how much time do we have? 9 minutes. Yeah, we're not going to get to that pulley one. We'll do it. I got 2 more quick learning catalytics, and let's go over. So this whole method, sketch and translate, simplify diagram, represent mathematically, solve and evaluate, is always the same for all these problems. What you do is sketch and translate, you make a little sketch. First thing you should do, draw a diagram. And I would do this even for the multiple choice questions. Draw a diagram. There's going to be a blank sheet that'll be at the back. You can pull it out and use it as scratch paper. Draw a diagram, pick your system, define your XY axes, and then put your knowns and unknowns on there. Sort of write down the things that matter to you. Okay, next step. Try to simplify it, maybe tell what your assumptions are, maybe ignore air resistance or something like that. Maybe there's something's frictionless. Keep a note of that. And draw a force diagram using the same sort of coordinates and things that you have from your sketch. Draw a second thing, which is force diagram. So it's going to be super important. If there's normal force, or if there's tension, or if there's static friction, there's no equations for any of these. So if you skip drawing the force diagram, you're never going to figure those ones out. They come from the force diagram. So this is why I do these 4 steps. And then so the third step is to try to write down Newton's second law. It's usually this, that you've got sum of fx equals m times ax, and you get the sum of fy equals m times ay. That's Newton's second law, basically. That's where your equations come from to solve out for normal or tension or static friction. And then you solve it. So sub in your values, try to get an answer. Sometimes you may want to check like I did that Bugatti thing. I was thinking, does this make any sense? Evaluate your work to make sure it sort of makes some sense. This is sort of the last step. Sanity check. Okay. It's good to do all these things and kind of get yourself into a habit. Like I say, if you're feeling stressed out in the middle of a term test, it's good to have routines, okay, and that'll calm you down, like eating that banana or drawing a diagram, that kind of stuff. Here's a learning catalytics question. What should you think about? Got 2 related questions once again. One is about a spring scale. So I want you to think about the force diagram here. And so I have a really good pizza dough recipe, which calls for a kilogram of flour. So I happen to have a spring scale that I always get out when I'm making pizza. So what if I were to measure the flour while I'm in an elevator that's accelerating upwards at 1.5 meters per second squared? How would this affect my pizza? Be a minute to think, pair, and share. There goes the timer. You guys got an answer? I'll give you another 20 seconds till I get this up to some number here. Sometimes you have an intuitive feeling, and then when you try to overthink it, you can kind of screw yourself up, but your intuition should be hopefully jibe with what's really going on, right? That's what we're trying to do here. Okay, go once, go twice, and stop. Let's do see what I'm seeing. Yeah, I liked that it's not enough. So what you might think is that you're going to feel heavier, and so it's going to be too much. But I think what's going to happen is that I am going to pour the flour until the dial says 1 kilogram. But the dial's reading high. Does that make sense? So I'm going to probably pour out like 0.8 kilograms, but it's going to say 1 kilogram because the I have it on the next slide here. For any given amount of mass, the spring must push upward more than the gravitational force from the Earth on the flour. And the spring is what's giving the dial on the scale. So the scale reads high. That's why you feel heavier. So if I see 1 kilogram, I should know in my mind that it's actually less than 1 kilogram of mass of flour. And what that's going to do is make the dough really runny and sticky, and it won't taste very good. So, okay, now I've got another one. What if I use a? Do you want to? Maybe we should show what a pan scale is. Can we? Is that ox plate? Quick little demo. You guys heard of a pan scale? So what this is it's just two things, and it compares masses. So if I put, that's 100 grams, there's 50 grams, but I put 100 grams on there, then it goes sort of in the middle. It balances itself out. And then you know the masses are the same. So people used to use these a lot for, I don't know, if people were paying with gold coins or something like that, you'd have your own, the vendor would have their own known mass on this side, and you'd pour the gold coins on this side, and when it was equal, then you'd know you had enough gold to set. So imagine now, I set this pan scale, I'm going to put, I know there's a kilogram on one side, I'm pouring flour onto the other side, and I'm on the same elevator. Let's go back to the slide. What do you think? Give you a minute to think, pair, share on that one. All right. You know what I'm seeing? Over here, I'll leave it on. I'm seeing 78%, so I'm liking it. You guys have the right intuition. Really impressed with this class. I think there's going to be a lot of people getting A's in this class. That's okay with me. So, is my thingy off? No, it's on. Okay, so what we're doing with a pan scale is simply comparing two masses. Sometimes it's rigged so you're comparing a ratio of two masses, but when you have the same mass on either side, it balances out. So it doesn't matter what the force of gravity is. It would still work on the moon, it would still work on Jupiter or something like that, and it would still work in an accelerating elevator. So I am going to do one more example from chapter 4 on Friday, because I want to do another Pully question for you, and then we'll be done. And I'll give you some hints about writing tests, and then we'll start in chapter 5, which won't be on the test. I'll see you Friday, I hope.